Hello, everybody. This is Dan Ambre from Full Spectrum Diagnostics. We're going to do a webinar today for Grace Technologies on gear-related problems and gear analysis. If you have any questions, go ahead and type those in the chat box. I believe there's a control for that, and we'll get to them as soon as I'm done speaking. It should be about 45 minutes or so. I tend to be long-winded, so I'll keep going as long as I can think of things, but we should fill up the hour. And we're going to start. Let me put this in presentation mode, get ready to go. There we go. Gear problems, problem detection, and data analysis. There's many important things that you need to know about gears. One of the things that's most important is the tooth counts, and we're going to talk about that quite a bit. If we don't know what the tooth counts are, we cannot trend and diagnose problems that are accumulated in our gearbox. We have to know the tooth counts. Tooth counts give us the meshing frequencies, they give us the speed of the internal shafts, all kinds of different information that can come out of that. I'm going to be talking mostly about gear problems in the frequency domain. Okay, but you also have to take time waveforms, and I'll mention that as we go along. So let's kick it off here. Gearboxes and gears. I have a little triple reduction gearbox down there at the bottom. Starts out at 1195 RPM, and it goes down to 35 RPM. So this is a really big gearbox that's used in the oil seed business for one of my customers. Crushes the sunflower seeds or whatever they're using to extract oils from. So gears are used to transmit rotary motion from one shaft to another. Gears are designed to change rotational direction, change speed, or increase the mechanical advantage between rotor systems. So key design parameters useful for the vibration analyst are rotational speeds, the input, the output speed. Usually those are the easy things to get. The internal shaft speeds are also very important because that's all part of the gear ratio in effect. But if we look on the nameplate of the gearbox, and it'll say the ratio is 0.045 to 1, that's meaningless for our applications. It's not telling us what the gear mesh frequencies are. It's not telling us what the internal shaft speeds are. It's giving us very little to trend. We can do an overall trend of the gearbox until we know what the tooth counts are, but tooth counts are required to do any good vibration analysis, any good trending, anything that's meaningful. Also, your shafts, and I don't show all the bearings here, but every shaft in here is supported by bearings. And the bearings will fail. I mean, just because we're looking at a gearbox doesn't mean all the problems are going to be gear related. They're also going to be, shaft related, like anything else. We can have misaligned gears, we can have loose bearings, we can have bearing defects that show up. So we need to know what kind of bearings are in there, manufacturer and model number, that type of thing. But we also need to know where to measure those for those bearing signatures to come out, okay? Every bearing, X, Y, and Z. If we can't get all three directions, we get as much as we can. And that's how we trend the bearings. The bearings are transmitters for all the meshing frequencies. So all the energy in every mesh, but I show a couple gears touching each other here, the energy is going to go through the shaft and in the bearings and out to our accelerometer, okay? So we might not be able to see these internal shafts. And in this application, I didn't even know what was in there until I got the drawings, okay? The drawings should give you the tooth counts. So internal gearbox supports, what kind of ribs, where are the bearings supported in there? That's where we want to take our data. The tooth design, what type of mesh is it? Like this is a spiral bevel 90 degree gear mesh in here. So the teeth are designed to transmit that load. There'll be some radial load, there'll be some axial load. A lot of times we don't know what's inside the gearbox, so we take measurements X, Y, and Z on every bearing. In fact, we'll discuss a little bit further as we go on. We're going to take two sets of data. One set of data is going to look at the health of the bearings on the inside, and we want to take those axial, horizontal, and vertical. And then at that same location, we're going to look at a higher frequency range so that we can see the gear meshing frequencies. And we'll talk about this later, but we're looking up to 3 gear meshes. So not 3 different gear meshes, but 3 times gear mesh frequency on each meshing condition. So these 2 gears are touching, they share a gear mesh. I'm going to look for 1 times gear mesh frequency, which would be, in this case, there's 31 teeth, so speed times 31, that's 31 times RPM, should show up in my spectrum. So if it's 1196, it's 1196 times 31, but I'm going to want to look at 62 times running speed and 93 times running speed. These are the 1, 2, and 3 times gear mesh signatures that will show up in the spectrum. And we'll get to why that is in a moment, okay? We want to know what the loads are in the gearbox. If you have varying loads all the time, you're not going to have very good trends. I did a job in a plastic extrusion. They used to make garbage bags, and they had 6 different settings, 6 different products that they were putting out. They all had different loads. They all had different speeds through the gearbox, different extrusion process, basically on the same gearbox. We'd go in there monthly, we'd take data, and the trend was all over the place because they were constantly changing what product they were producing, and we never bothered to take a look and see, what that effect was. But pretty quickly we found out, hey, we're not getting good trends. It's really high, really low, it's bouncing around all over the place. We decided to go in and make 6 routes, and each route would be a different product that they'd be putting through the extrusion process and through the gearbox loads. So now we had 6 trends, and they were all very good. Took a little longer to produce that many, taking data once a month, but they were all really good trends, and it was a great idea to do it that way. Natural frequencies. Natural frequencies in gearboxes usually come from looseness, misalignment, backlash, things like that, any normal type fault that you'd see in any rotating system. But in this case, it might ring the gear. So a little looseness in the gear mesh, you get a little chatter, you're hitting one tooth face on the other, and you excite natural frequencies. It's like ringing a bell. They have an interesting signature in the spectrum, and we'll look at that as well. So temperature, operating temperature, what lubrication we're using, what material properties, where the bearings are, what is the bearing design. There's thrust bearings or the spherical rollers. A lot of times are used in applications like this because there is some axial component. There's a lot to think about, okay? Your normal fault patterns for all the bearings, and now you lay on top of that all the gear meshing faults that can occur. And there's, I believe, 6 different kinds of faults that we'll be looking at. So what is a gear mesh frequency? Gear meshing frequency is a pulsation force generated when the gear teeth come in contact and is equal to the number of teeth times RPM of that gear. Very simple equation. The shaft that's spinning, that's the RPM we're interested in. The shaft that's spinning has a gear on it with a certain number of teeth. We're interested in that. It's touching another gear. They share a gear mesh frequency, and it's easy to calculate that gear mesh frequency. It gets a little confusing, but the math is very simple. We're going to walk through one as we go. A lot of people will do just ratio of gear teeth all the way through the gearbox, and if you're a gear guy and you use this all the time, that might be what you need to do. If you're not, you're less likely to make an error if you go the long and drawn out way that I'm going to show you. You would rarely make a mistake with this method, okay? In a gear train, there's 3 forces as each tooth comes into mesh. Now each tooth, you might have 31 teeth on the gear, each tooth will come into contact per revolution of that gear. And some people can't get their head around that quite. But as each tooth goes into contact, there's 3 things that occur. There's a sliding into that initial contact. it'll roll about the pitch circle, and then it'll slide out of engagement, okay? And then on to the next tooth. And 31 teeth later, if you have 31 teeth, you've made one revolution, okay? So the meshing frequency is how often this sliding, rolling, sliding goes into effect. And that depends on the tooth count, okay? Now, the other thing is I have down at the bottom 3 different spectrum, X, Y, and Z, axial, horizontal, vertical, and 3 time waveforms. And what I'm showing in the spectrum is the 3 gear mesh harmonics, okay? 1 times gear mesh, 2 times gear mesh, 3 times gear mesh. Why do I do that? I have 3 faults that are occurring. When I have a rough gear tooth surface, it's not sliding anymore, not like it was designed to do. If I have lack of lubrication, I might be wearing the gears out. If I have, I've ingested something, somebody dropped a bolt and went through the gearbox, I might have a broken tooth that's going through the mesh, okay? There's a lot of things that can change, but looseness, misalignment, eccentricity, backlash, those are affecting these 3 forces. So in effect, they're affecting what's the amplitude of these 3 forces in the spectrum. So we're always going to look up to 3 times gear mesh. In fact, we go a little higher. We go 3.25 times gear mesh frequency. So we calculate this first one. We set our frequency range 3¼ times higher so that we can capture all 3 and that we can see the sidebands around them, okay? I've put this on a log scale so that you can actually see it. In this application, you know, you can see the gear mesh frequencies in the log scale. When you put it in the linear scale, you can't see them nearly as well, okay? So if you are doing some analysis, logarithmic scales really help bring out the peaks. And also, if you zoom in and look for sidebands, it's a nice technique for that as well. Okay. Gear mesh frequency, not necessarily a problem. Low levels are normally present, okay? These are low levels. My amplitude scale is 0.1 inches per second, and we're all well below that, okay? So this is a pretty good running gear. This is the time waveform of each one of those. And this was a special application. I have 2 seconds of data, but in all actuality, when I took the data, I had a 16-second time waveform. Really long one because the very low frequency. And what we're looking for is this pulsing event. We're looking to compare the amplitudes, and we compare the pulsing in the gearbox. So sometimes a cracked or broken tooth might show ringing patterns like this. Okay, in this case, the levels are pretty low. It was just minor inconsistencies in the surfaces of the gear that were showing up. All right, I have a double reduction gearbox, and I'm gonna throw a little math at you. Keep an open mind. It's fairly easy to perform these calculations. There's really only 2 different equations we're going to use over and over again, okay? Governing equations down here, number of gear mesh frequency is the number of teeth times RPM. So what does that mean? My input shaft is turning at 1790 RPM. It has 28 teeth on its gear. It's touching another gear. There's a gear mesh. Here's another gear mesh. This intermediate shaft in its gear is touching another gear on the output shaft. So I have 2 different gear mesh frequencies in this box. How do I calculate gear mesh frequency? Input speed, whatever this is, speed of the shaft, S1 times 28, and I get my gear mesh frequency. Since these 2 teeth are 2 gears are touching, they share a gear mesh. Okay, right? And I know all the gear teeth. Input's got 28, the intermediate has 18 and 12, and the output has 59. We're going to walk through this calculation over and over again, okay? This one is the same thing. It's basically saying gear mesh equals gear mesh. Since the 2 teeth are touching, or the 2 gears are touching here, it's 1790 times 28 equals 18 times whatever the speed of that intermediate shaft is. And that's one of the unknowns that we're going to solve for in a moment. Okay. 2 gear meshes in this box. The tooth counts must be known. The governing equations are shown below. The gear is typically larger with a higher number of teeth. The pinion is typically smaller with a lower number of teeth. Okay. Measurements are collected at the shaft bearings. So here I show my bearing supports. So all the energy has to go through the shaft. It's a very good practice to take data X, Y, and Z, or axial, horizontal, and vertical on each bearing for the bearing health and for the gear health, because I don't show any thrust in here, but there might be. Okay. Example, the calculation formulas. Gear mesh frequency 1, it's the first equation down here. It's the number of teeth times RPM. So gear number 1 and gear number 2 are touching. Down here, gear mesh frequency 2, this gear number 3 and gear number 4 are touching. Okay. So they share a gear mesh here, they share a gear mesh there. And we can use the ratio of the teeth to calculate what the speeds of the shafts are and what the gear mesh frequencies are. So I show something a little more complicated than you really want to see, but we're going to walk through it real easy on the next couple slides. So gear mesh frequency equals the number of teeth times shaft speed, so 1790 times 28, which is here. And it also equals whatever the intermediate shaft speed is and the 18 teeth. And what we're left with is we don't know what the speed of the intermediate shaft is. We bring our tooth count down here and look at the ratio of the one gear to the other, and we get our speed. Okay, sounds ridiculously hard, but it's very easy. Same thing with the gear mesh frequency number 2. If we calculate the intermediate shaft speed, we multiply it by 12 and we get this meshing frequency. And then we end up dividing by 59 to get the output speed. Okay. Gear mesh frequency 1, 28 teeth, 1790 RPM. We multiply those two together because that's our governing formula for gear meshing. I get 50,120. Okay. That's the gear mesh for this shaft and for this shaft. So those two are touching, they share this gear mesh frequency. Okay. 28 teeth times 1790 is the gear mesh frequency. The output, the intermediate shaft is 18 teeth, and its speed is unknown at this point. So I divide both sides by 18 teeth, which I have down here, and I get 2784. That's the speed of the intermediate shaft. Okay, so I calculate the gear mesh frequency, which is 1790 times 28. Since they're touching, they share a gear mesh frequency. So I divide that gear mesh frequency by 18. I get the speed of the intermediate shaft, the unknown in this equation, and it's 2784. Okay. Gear mesh frequency 2, 12 teeth, 2784 RPM. That's what we just found, what we just calculated was the intermediate shaft speed. Multiply those two together, I get 33,412. That's the gear mesh for this shaft and this gear, and for the output shaft and its gear. Okay. I know the number of teeth on the output shaft. So I have the input shaft is 12 teeth times 2784, teeth times RPM equals teeth times RPM. I have 59 teeth. I don't know what the output speed is, or the shaft number 3. I divide my gear mesh basically by 59 and I get my output speed. Okay. Output speed is 566 RPM. Okay. If you walk through it, it's as long as you know that these two shafts share a gear mesh frequency and you know the tooth counts, you can walk through any gearbox. Well, a little caveat, planetary gearboxes are a little different animal, but you can solve any normal gearbox, any reduction or what have you type of gearbox. Now, let's get crazy. How many gear mesh frequencies are in this rotary screw compressor? These are lobes. These are the rotary lobes, and there's a male and female, and they are not gears. These are gears in here. So how many gear meshes do I have? You're going to say, well, there's a gear set here. There's 1 and 2 and 3 and 4, right? But what about this guy? Maybe that's one more, because those are 2 teeth touching, right? So I have 1 set here. So 1 gear mesh, 2 gear mesh, 3 gear mesh, 4 gear mesh, 5 gear mesh. Okay, wrong. It's not 5, it's 4. This is 1 gear mesh. There's different speeds, but if this tooth is touching, or these teeth are touching these teeth, they share a gear mesh. If this is touching this, they share a gear mesh. So these are 2 different stages, different tooth counts, but the meshing frequency is the same. Okay, just because they're touching each other. Okay, well, that might bring this point home a little bit easier. The top set of gears, there's 6, 7, 8 different gears on there. Okay, how many gear mesh frequencies are there? Each one is touching the other. So number of teeth times RPM is touching these gears, and we can see what the RPM of this shaft is and walk all the way through. But this shaft is touching that shaft, that one's touching this one, and so forth. All the way through, there's 1 gear mesh. Okay, depending on the tooth counts, there's up to 8 different speeds that we'll see in our operating response, but only 1 gear mesh. Now, which gear is causing the problem? It's going to have to be something that's local. So I'm going to take data on the bearings of each of these shafts. So if I have a gear meshing problem, it's typically the one with the largest amplitude, okay, from my survey. Same thing here. This is it doesn't look real good here. It's some flaw in the animation, but this is a rotary screw compressor, or lots of different types of compressor with multiple stages. So I have a bowl gear in the middle. It's touching each of the pinions. So I only have 1 gear mesh frequency. Okay. We go back to our example. I can see these are independently touching each other. There's 1 gear mesh. Here's another one. There's a 2nd gear mesh. Okay. These are all touching. This is a bowl gear, and this is 2 different compressor stages. I have a gear mesh. 1 gear mesh frequency will show up for these 3 gears. These are independent of a bowl gear or anything like that. So I have 1, 2, 3, and 4 gear meshes. Okay. This webinar is being recorded. So if you're a little confused, you can, after the webinar, give them a couple hours to put it all together and get it back on the internet, and you can watch it as many times as you like, and hopefully it will help you understand a little bit. Typical gear problems. We have several things that can go wrong in a gearbox. Excessive tooth wear, which is basically looseness. Operational load variations, which really isn't a problem, it's a trending issue. I mentioned the extruder, gearbox, the 6 different conditions. Operational load depends on what your product is, what your load is. Okay, most gearboxes just run one process, and you don't have to worry about this. But if you do have various processes going on, different speeds and loads and so forth, that can really affect the spectrum. Eccentricity and tooth backlash. This is when the gear wobbles. So it's very similar to a pulley on a belt drive system. If the hole isn't drilled right down the middle of the pulley, it'll wobble every revolution, and you'll get a lot of stretching issues and failures in the belts. Same thing can happen in a gear. It can be off center slightly. The hole through the middle is off center to the outside of the gear, and the gear will wobble. Okay. If you the only way to solve that is to get a gear that doesn't wobble anymore. but it'll show up as eccentricity and backlash, and there's a specific spectrum for that. Same thing with gear train misalignment. The gear can be misaligned, the whole shaft, and it'll affect axial and thrust direction motion in the gear. Loose gear or bearing fits. Mechanical looseness type C is a bearing problem where the bearing is loose on the shaft or loose in the housing, and it can show up in the spectrum. Same thing with the gear. You can see a bearing fit problem, but you can also see a loose gear, oversized keyway, things like that that'll show up in gearbox applications. Cracked, chipped, and broken tooth problems. These are rarely seen in the spectrum. They show up in the time waveform. And in the time waveform, it'll look like a pulse every revolution of the gear. And we'll talk about that in a sec. There are two more complex problems. There are tooth repeat problems. One is called a gear assembly phase frequency or wear pattern, and one is called a hunting tooth repeat problem. Okay, typically we don't talk about these in an entry-level type class, but there are formulas for them that help you identify them. Okay, there'll be peaks in your spectrum that'll show up that you don't know where they came from, and a lot of times it's either assembly phase or a hunting tooth problem that's showing up. All proper analysis requires collection of special spectrum and waveforms. So above and beyond your bearing defect spectrum that you're collecting, that's going to be in a certain frequency range for bearing failures. You're going to now have another set of data that's a little higher frequency, and it's going to cover that 3 times gear meshing that we talked about earlier. One thing you can do for gear-related problems, you can have special spectrums. What I'm showing down here at the bottom is a envelope spectrum. They call them different things, but basically it's a statistically set threshold level for multiple gearbox applications. And in this case, I had several gearboxes that were identical. They're all running in the same area, and I can look at them statistically as a family instead of just a one-off type thing. And the beauty of that is if something's out of family, you're going to see it much quicker. Okay, so most software out there will have statistical bands or the ability to do that. In addition to taking your normal data, it's just another set of alarm bands. You have standard ones, and then you'll have another one that says, hey, is this in family with the rest of the gearboxes? And it's a very helpful tool. So what are we going to see in the spectrum? We're going to see running speed multiples of gear meshing and rotational speed of the shafts. So there can be any type of normal misalignment and looseness that you'd see in any system. We might see natural frequencies poke up in gearboxes that have broken tooth problems or eccentricity or backlash problems. We might have sideband modulation, so eccentricity and misalignment, spacing errors, wear on the gears, and sideband modulation will show up as frequencies plus or minus rotating frequencies of the shaft. So I'll see a gear mesh peak in there, and then I'll see sidebands like this. So plus or minus 1 times RPM, plus or minus 2 times, what have you. And you'll get a little haystack of defined frequencies, and you go in there and see what the source is. The sideband spacing will tell you whether it's the input shaft or the output shaft, but overall it'll tell you have some type of issue going on. Hunting tooth repeat problems, we're not going to talk about those in this webinar, and sub-harmonic wear patterns are assembly phase problems, a little too complex for kind of an entry-level look at gears. Here is a series of time waveforms, and what you're seeing is a broken tooth in the top case, and it's been running for years, actually decades. I originally looked at this in 1996, I think, 1995, something like that, and it's still running. So it thumps, and every revolution of the gear, there's a crack, or a missing tooth or something in there that is pulsing. So it'll ring it, and it'll ring down like you're ringing a bell, and you'll get a very unique look. And this is the spacing, so it's telling me I have one cracked or broken tooth. Every revolution of the gear, when it goes into mesh, that tooth causes a different problem, either a pulse or an empty spot. Modulation, so there's transient pulses, cracked or broken teeth. Modulation in the time waveform, you have this sort of signature. So if I went from here to here, that would be one revolution of this gear. Okay? If I counted all the peaks from the middle of this lobe to the middle of the next lobe, I believe there's either 27 or 29. So I have a gear with 27 or 29 teeth on it. Okay, but this is okay. You should see something like this. Nice defined meshing frequencies. There's no big transients. You'll get a little modulation from imperfections in the gears. Okay. The last one, this was a gearbox that ate a bolt, and they started it back up, and it was pulsing out of family. So you get cracked or broken teeth, you'll get transient pulses. If you look closely, you can see truncation of the peaks. If I zoomed in on this, all kinds of different looks at it, but basically you can see right away, it's not smooth like this one, it's pulsing. And if you put your cursor on it, it's turning speed of something, input shaft, output shaft, intermediate shaft, and you should be able to identify that. Okay, normal gear spectrum, you're going to have gear mesh frequency. It's going to be in a low amplitude like this, and it's going to tail off. So we're going to take a high enough frequency range that we can see 1, 2, and 3 times gear mesh, those 3 multiples. They're going to follow this type of trend, kind of an exponential decay of energy. Okay, so I should see 1 times RPM of the shafts in here. It's not my real concern in this spectrum. I'm more concerned with the gear meshing. So each shaft will have low harmonic multiples of the turning speed. No gear natural frequencies. Gear natural frequencies, you might confuse a gear mesh with a natural frequency, but they'll show up anywhere. If you know the tooth counts, you know where this is, okay, where the gear mesh frequencies are. No excessive floor noise, low amplitude 1, 2, and 3 times gear mesh. Relative amplitudes diminish at higher frequencies, which they do. Low amplitude sideband sets surround gear mesh frequency spaced at 1 times RPM. If I zoomed in on this area and had enough resolution, I'd see sidebands at turning speed of each of the shafts. In this case, they're very low. You look at the amplitude level. They're less than 0.01 inches per second, which is extremely low. Sidebands should be equal and symmetric in appearance. The real heavy hitter thing that I want you to throw into your memory bank is set the Fmax at 3.25 times gear mesh frequency. So I go through I get my tooth counts, I calculate the gear mesh frequencies, and then I set my trending Fmax to 3.25 times whatever that gear mesh frequency was. So I have range to be able to see these 3 peaks and the changes in those peaks. Normal gear waveform, and this is a fairly good modulating gear, slight imperfections in the blades, but I can go into my time waveform, and this is 1 revolution, 2 revolution, 3, 4. So I'll get a repeating pattern every revolution, and there won't be any transients to speak of. It's pretty constant waveform. Okay, key thing here, set the time max to collect 6 to 10 shaft revolutions. And there's an equation for that, and I don't think I included it here, but you just calculate how long it is to go 1 revolution, which you see here, and multiply it by 6 to 10. And that's the time waveform that you want. I have 1, 2, 3, 4 revolutions of the shaft. So I defied my own rule by not getting enough data. I want 6 seconds, not 4 seconds minimum. Tooth wear, numerous sideband sets at speed of the worn gear. So the sideband sets are here. So I have my gear mesh 1, 2, and 3 times gear mesh. I'm going to generate, as looseness gets worse and worse, more sidebands, plus or minus 1 times RPM of whatever either gear or pinion is loose. It can be looseness in the tooth-to-tooth spacing. It could be looseness in the gear on the shaft, over or undersigned keyway, things like that. Okay, so looseness comes in a lot of form. It'll generate wear, and we'll see it as additional sideband sets. Now the other thing is 1 times gear mesh and 3 times gear mesh are typically higher than 2 times gear mesh. In this case, the wear is on that sliding in and out of mesh. Remember, you slide, the tooth slides in, pitches, it revolves around the pitch circle and then slides out of contact. So if there's wear there, it doesn't, the sliding effect isn't nearly as good, and you'll start to get increases in your trends of 1 times and 3 times gear mesh frequencies. Okay, another interesting thing, oil analysis for wear particles. If you have a good oil problem program in your plant, and you're actually taking samples every month or what have you on your gearbox, you're going to pick up indications of wear much quicker than you will with vibration analysis. Hand in hand, they're both really good to have. You really shouldn't have one without the other, but the oil analysis is going to pick up those particles that are the wear patterns that are coming off your teeth. They're just going to go in the oil, and you're going to see it quickly. Okay. Also, it's good to perform visual inspection of gears for variations in the load wear patterns on the tooth face and things like that. This was a case history. This was a generation of peaks that fooled me. It was a compressor, and it had so many teeth on the compressor gearbox, and I didn't know what that was. This is actually where the gear mesh frequency was. I thought the gear mesh frequency was this peak, but I didn't know the tooth counts. This turned out to be a gear natural frequency, which looked a lot like a gear mesh frequency problem. This compressor that was driving a chiller or driven compressor, one of them failed once. I don't know what it was. It wasn't due to vibration. It was something else. They took it apart, and they had the gear out sitting on a pallet. And I went and counted the teeth, and I'm like, oh my gosh, this is not the gear mesh frequency. And it turns out that this was the gear mesh frequency down here. So I had a nice pattern, and what I was seeing wasn't a gear problem per se. It was something was ringing the gear. And what I saw was this. If I zoom in on it, I see a peak, I see sidebands, and these sidebands are running speed at one of the gear shafts. So it looked like a gear mesh frequency to me. And what it turned out to be was some looseness in the gear train, a little backlash that was ringing the gear. And this is blade pass frequency of the compressor. So this signature can show up anywhere. If it's a gear natural frequency, it's based on mass and stiffness. So it doesn't have to be anywhere. It just, whatever the mass and stiffness distribution is, and whether it's excited or not, are the parameters. Tooth load, and we talked about the extrusion process and the low-speed gearboxes. Amplitudes will vary. That's what we're mostly looking at. So we can see changes in 1, 2, or 3 times gear mesh. Usually 1 times is one of the things that will be more variable. We should see some sidebands, but it's a case of not trending on uniform loads. So I always get in trouble with people from paper plants. I say trending should be performed at the same load conditions every time you take data, and they just laugh because that never happens in a paper process. But in this case, that's what you need to do to get good trends. And you can do it. You can make multiple trends if you need to. Problems are typically indicated when sideband sets and gear natural frequencies appear. Okay, so gear natural frequencies can appear anywhere in here. I'm not showing one, but it can be anywhere. It's frequency and mass governed. Remember to capture a time waveform, check for cracked teeth, often from overload conditions. Okay. This is a tooth load phenomena, and this was that process that we talked about earlier. This was the extrusion process. And you can see the 1, 2, and 3 times gear meshes over time. This was 3, 6, 9, 10 surveys. So it's almost a year of data, and they're bouncing all over the place. So there's not a good trend in any of the harmonics. So that's where we went to, we considered it all poor trends, and we went to started one at a time, different routes. Some of the goals here, variable loads create poor trends. 1 times gear mesh is very sensitive to load. Minimum 80% load should be maintained for all trending conditions. Repeat load conditions each survey, and you might need special routes to do that. Gear-related problems, backlash and eccentricity. These will generate changes in sidebands. So you'll see a couple of things here. You don't see that normal progression. You see 1 times and 3 times gear mesh are a little higher. You also see sidebands around the gear mesh frequency. And typically, uneven sideband sets can occur. Usually the high frequency sidebands are higher in amplitude than the low frequency side. They don't have to be. This just some of the symptoms: high 1 and 3 times gear mesh, sideband sets that usually are there for eccentricity problems and backlash problems, but they can have a lot of different signatures. Also, gear natural frequencies might be excited. So I showed one of those in here. This is an actual measurement, and it didn't show high 1 and 3 times. It actually showed a high 2 times, but it was a backlash case, and it was a failed gear system. It loosened everything up. Hard to explain what the problem was, but it was pulsing, and I captured one of the pulses. But the frequencies were very interesting. So they didn't follow your normal backlash condition, but they did generate a natural frequency, and it had sidebands. So this looked like a gear type related problem, but it was a natural frequency. This is gear misalignment, and you don't see this a whole lot. I've seen it a few times over the years. This is a set of data from 2 times gear mesh, and we'll get to that in a second. This is what you should see. You should see a high 2 times gear mesh. You should see some sidebands, and the lower frequency side should be higher in amplitude than the higher frequency side. Not in all cases, but it usually occurs that way. High 2 times gear mesh frequency. This was I'm monitoring currently a process in a cement plant, and it's a big drum. They call it a raw mill, and inside there's steel balls, and they're crushing the rock into powder, basically. And I've been monitoring it, and the only frequency of interest was this 2 times gear mesh frequency. So this big rolling horizontal drum is finding its happy place, in a sense. Every time we shut down, it'll start back up at a different amplitude level, but it tends to start this trend of smoothing out over time. And there was some variability here. They couldn't get their conditions right, and they kept shutting down like every 6 hours or something. But there were long stretches of it like this. And the 2 times gear mesh frequency was the only thing in the spectrum that was high. Okay, and it was acceptable, but it was still high compared to everything else. So misalignment typically indicated by a high 2 times RPM. Highest amplitude is 2 times gear mesh frequencies. You might have sidebands that are spaced at 2 times RPM around the gear mesh frequency harmonics. Uneven sidebands can occur. Misaligned gears are indicated by the spacing of the sidebands. And if you look at it visually, you'll probably see uneven wear patterns in the gears, in the gear teeth. And I think this is the last one, the cracked or broken tooth. You will not show up in the spectrum. You might see a natural frequency that shouldn't be there, and you will see the gear mesh frequencies in the spectrum, but you won't see a broken tooth because it's occurring at turning speed of the shaft. So if I have one broken tooth, every revolution, it'll go into mesh and it'll generate something at 1 times RPM. Okay? We might see a slight amplitude change, but the averaging process from the time domain to the frequency domain kind of averages any amplitude variations out. The best way to look at it is in the time waveform. This is showing the red line here is a set of gearboxes. Actually, the whole thing is a set of gearboxes. There were 6 of them. 5 of them behaved like the red line here, and I overlaid the blue one, which had a problem. It was an open gearbox and dropped a bolt. Somebody dropped a bolt in it, and it chipped one of the teeth on the gear. And this was an intermediate shaft, and you could see it pulsing, and the pulse rate was at the speed of the intermediate shaft. So we knew right away where it was. Got a strobe light out, and we did a slow roll with the strobe light, and we found what tooth was the problem while it was still running. Okay, we need 6 to 10 revolutions to see something like this. Okay, so we need to know what the speed of the internal shafts are, the input speed, the output speed, and we need to take a sample that's 6 to 10 revolutions so we can see a repeating pattern. If we take a too short amount of data, we're not going to get a good idea of what's going on. If we take too long, then we lose resolution. So 6 to 10 revolutions is our best bet for that. And the last one, loose fit problem, not really a gear problem, but it'll turn into a gear problem. So we can lose our fit on our bearings, on our gear to the shaft, loose keyways. We get basically mechanical looseness type C, which usually shows up as low frequency harmonics, not gear mesh frequency. But we do have an odd change in the gear mesh frequency distribution. Instead of going down, they tend to go up as you go higher in gear mesh frequency. Not actually a gear fault, but can result in gear damage if not corrected. Okay. Couple of gearboxes. And you can walk through this. Basically, it's gear mesh frequency is RPM times the number of teeth. So 720 times 47 will give me this gear mesh frequency, and then I'll have another gear mesh frequency here. And there's 2 shafts, so all these 3 are in contact, so they share one gear mesh frequency, and these 2 are in contact across here, and they'll share a gear mesh frequency. This is the calculations for the gearbox that we started off with. This is a really complicated gearbox, but you walk through step by step and you can get yourself to the end. You just need to know the number of teeth on each gear and how they're mated. I appreciate you joining me, and we'll probably be doing more of these in the future. But if you liked it, send me a note. My email address is modalguy@aol.com, modalguy@aol.com. Yeah, I know I'm the last guy in AOL. Don't want to hear about it. So give me a call if you need to, and especially the people that wrote some of these comments that I couldn't decipher. I'm sorry about that. The size of the block for this is very small. But that's all I have.